So today let's talk about heat pumps. When you first hear the word heat pump, that sounds funny, doesn't it? What? I know water pumps, but heat pumps? Well, it's a similar idea. What you have is you have power or work being supplied to a system, and the purpose of the system is to really dump heat into a high temperature sink or high temperature reservoir. This is the goal of a heat pump. Now you say, well, if I want to heat something, let's say the inside of my house on a cold winter day, then a lot of homes in San Antonio basically come in and they have electric resistive heating, or apartments in San Antonio, Texas have a lot of electric resistive heating. But if you put in, let's say, a kilojoule of electricity, work, or energy input, how much heat would you get into the air to then heat your home? 1 kilojoule. Can you do better than that? Sure, if you have a heat pump. So in the heat pump, maybe you put in 1 kilojoule of energy, and maybe you get 3 kilojoules of heat delivered into the house. So how does this work? Well, it's just the air conditioning system run backwards. And actually, a lot of them, they'll just have valving, and they'll have the same evaporator, same condenser running, and they'll just change a little bit, okay? So that they'll actually switch what is happening in the condenser. It'll become the evaporator, and the evaporator will become the condenser, okay? But just think of a dedicated heat pump system. So let's study that first. It's air conditioning system. It's the same compressor, condenser, expansion valve, evaporator. The only thing is, instead of this being the goal, cooling, this is the goal, heating. So what did we have for a coefficient of performance for a heat pump? Let's compare it with the coefficient of performance for a refrigeration system. Both of them are what we desire over what it costs to run. So let's say the work to run the compressor, the work to run the compressor. But what do we desire? We desire a large Q delivered to the high temperature, and we take a large Q out of the low temperature. All right. What is the relationship between these two COPs? 1. That's the relationship. Let's go ahead and establish that. So if I say that for an energy balance, is the Q going out to the high temperature, is it equal to the Q coming in from the low temperature plus the work coming into the system that drives the compressor? Is that a true energy balance for the overall system? First law. So what we can do is we can replace the definition of the COP HP will be QL plus WC divided by WC. Let's work only on the left-hand or right-hand side. So that'll be QL divided by WC plus WC over WC. That's equal to COP of the refrigeration system plus 1. So the coefficient of performance of the same system, it's just the perspective. If you're focused on refrigeration, you get a COP for the refrigeration. If you want it for the heat pump, you just add 1 to it. Okay, makes sense? Ready to solve a problem? Very similar to air conditioning. So we have refrigerant 134A is a working fluid in the vapor compression heat pump system with a heating capacity of 20 kilowatts. What are they telling us in that 20 kilowatts? Is that Q dot to the high temperature? Yeah, that's what's happening. Is the Q dot happening, is this in the evaporator or condenser? That's the heat transfer. Is that happening in the condenser or the heat transfer that's happening in the evaporator? Condenser. It's in our condenser. So maybe Q dot in the condenser. It's what comes out of that refrigerant and is dumped to a high temperature source or sink. the inside of your house. Okay. The saturated vapor exits the evaporator at -12. So let's probably go ahead and make a sketch of the components again. You sketch it a number of times, you get better at it, right? So this is our condenser. This is our compressor. This is our expansion valve. This is our evaporator. Flow goes like this, to this, to this, to that. Let's call this state 1, state 2, state 3, state 4. And so we know what this one is right here. Q dot in the condenser is 20 kilowatts. And they say that the saturated vapor exits the evaporator at -12. So here is the T1 is -12 degrees C, and it's saturated vapor exiting. Saturated liquid exits the condenser, so saturated liquid at state 3 at a pressure of 900 kilopascal. The compression process is adiabatic, so you might want to emphasize that Q dot down here for the compressor is equal to 0. And the temperature at the compressor exit is 50 degrees C. So T2 is 50 degrees C. Determine things like the mass flow rate of the refrigerant, the compressor power, the compressor isentropic efficiency of the compressor, and the system coefficient of performance, COP, and it's a heat pump. So those 4 things we want to calculate. Make a table of the properties, and so state 1, 2. Now 2, because it's funny the way they've worded it. Do you think that it's isentropic compression in the compressor? If they ask you for part C to calculate the isentropic efficiency, it's probably less than 100%, isn't it? So you probably want to have state 2S and 2 actual to analyze that what's happening across that compressor. And then state 3 and then state 4. Let's talk about pressure in kilopascal, temperature, degrees C, quality, enthalpy, kilojoules per kilogram, entropy, kilojoules per kilogram Kelvin. All right. Have you done these enough? Does this look pretty easy? Let's march through the system. A lot of times we can fill in the pressure column pretty quickly. So we know the pressure at 3 is 900 kilopascal. How about the pressure anywhere else? 2? Is that 900? 2S, 900. So what is pressure at 1 and the pressure at 4? They're equal, but what are they? The saturation pressure at a -12. Table helps us in the appendice, and we pick up that it's around 185.4, 185.4, about 1.854 bar. That's with the temperature -12 degrees C, -12 degrees C. What do we anticipate about state 4? If this is coming in saturated liquid, we sketch it on a temperature entropy diagram. We have a line of high pressure, a line of low pressure. There is state 1. There is state 2S. There is state 2 actual. Here is state 3, saturated liquid at that high. And where is state 4? In the dome. It's 2-phase. It'll be down here. So we anticipate a quality at 4. Maybe 20%, 15%, 30%, 35%, something. But it's in the 2-phase. So that was a little fast on, hey, I know the pressure at both 4 and 1, and I know the temperature at 4 and 1. Okay? Does that make sense? All right. Now, if you want, we'll leave this quality. Really, the only quality I really care about is this. It'll be at the state 4. The rest of these will be zeros, 1, or non-applicable. Okay. Let's go ahead and get the enthalpy at state 1. It's saturated vapor. That's H of G, true? And so H of G, you can look it up, at that temperature of negative 12 degrees C. It's 240.15. Does anybody have a table appendix and they can just double check me? If you can't find 240.15, then raise your hand and say, help me a little bit. Where did I find that? That's H of G at a temperature of negative 12 for the refrigerant 134A. Then likewise, S of G, 0.9267. Those are straight out of the tables. So we have the isotropic process, 0.9267. So state 2, S, is fixed by knowing the pressure and the entropy. And we get this enthalpy right here, this enthalpy at state 2. And you find it 272.84. Here it's superheated. And now that we go and we calculate the minimum work for that compressor, the work of the compressor, if it was isentropic, will be H2S minus H1, which comes in at 32.689 kilojoules per kilogram. We have the isentropic efficiency of the compressor. Well, we don't know that, do we? We're going to have to calculate that. What do? They make it a little challenging because they tell us the exit temperature at 2. So they tell us the exit temperature at 2 is 50. If you do the linear interpolation, the same linear interpolation for the enthalpy and the entropy, you get that the actual isentropic temperature leaving is 41.4. So this temperature here would have been 41.4, but it goes out at 50 at state 2, a higher temperature. So now that we know the pressure and the temperature, we actually get the enthalpy coming out. It's 282.34 kilojoules per kilogram. So at this point, we get the work of the compressor actual, H2 actual minus H1, and that's going to be 42.190 kilojoules per kilogram. And guess what? I can now calculate the answer to part C, the isentropic efficiency of the compressor. Won't it be the ratio of those two? So it'll be the minimum work divided by the actual work, which gives us an isentropic efficiency of 77.5%. All right, let's go to state 3 now. State 3 is saturated liquid at that pressure. And so what about the temperature at 3? Tsat at that temperature, it'll be like 35.5 degrees C. And what is the enthalpy? HF, saturated liquid, which is 99.56. I really don't need the entropy, so I'm going to leave it off. But I need that enthalpy, right? 99.56. Do you see that? Did you find it? Stop me if you don't find it. Everybody find it that has tables? Good? All right. Now, how do I find the quality at state 4 and then find the enthalpy at state 4? It's like a two-step process because at state 4, we know the enthalpy and the pressure. So this is 99.56, right? And you can then calculate the quality at state 4 if you like. The quality at state 4 is 31.7%, meaning 31% by mass is now in the vapor state, leaving, what is that, 68.3% in the liquid state by mass, ready to evaporate in the evaporator to provide and pick up heat. You're going to pick up heat from the cold outside, which seems really funny. You're actually, in a heat pump system, you're actually cooling the cold winter outside. The air outside is being cooled by your system because it's drawing heat out of it that's being combined with electricity, and that's now dumped into your house to keep you warm in the winter. It's funny, isn't it? Anyway, let's press forward. So let's see. I think we can calculate the refrigerant mass flow rate. So the refrigerant mass flow rate, if we analyze, we needed 20 kilowatts up here. So Q dot in the in the condenser is the mass flow rate of the refrigerant times the H2 actual minus H3, and we have both of those enthalpies, H2 and H3. The only unknown that we don't know in this, we know the H2, the H3, and the Q dot. Only thing we don't know is the mass flow rate of refrigerant. And so you need the 60 seconds because it's, let's see, do they want it in kilograms per minute? So you can calculate it in kilograms per second and then multiply by 60 to get kilograms per minute. And it comes in at 6.565 kilograms per minute. 4 digits excessive, but you won't lose any points. That's the answer to part A. What is the compressor power? So W dot in the compressor is the mass flow rate of the refrigerant times the enthalpy 2 minus enthalpy 1. That look good? So the power to run the compressor turns out to be 4.62 kilowatts. So if you ran that for 1 hour, how many units of energy, of electricity would you have had to pay for? You'd have to pay 4.62 kilowatt hours. What's the value of that? What do you pay for a kilowatt hour of electricity in San Antonio? Roughly about 10 cents. So if you ran that system for an hour, it would cost you 50 cents. Let's press forward. Then the coefficient of performance, I'm running out of room. Let me recycle a little bit right here. COP for the heat pump system is what we desire. A lot of cooling, which was 20 kilowatts. Not a lot of cooling, a lot of heating. Kilowatts divided by what we had to buy, 4.62 kilowatts of power, electric. So the COP for the heat pump comes in at 4.33. Okay, here are the numbers for this problem. So you can see that the answer for part A, answer for part B, answer for part C and D. Here are all the enthalpies, entropies, if you want to flush it all out, as well as temperatures and pressure. Okay. Well, we have a rating for air conditioning systems. That was the EAR, or the SEER, the Seasonal Energy Efficiency Ratio. You have the Heating Seasonal Performance Factor, HSPF. Doesn't roll off my tongue as easily as the SEER, but it's a metric. And here it is, it's the Heating Seasonal Performance Factor is what you want, and that's Q dot into the high temperature inside of your home divided by W dot into the system. But this has the units of BTU per hour, and this has the units of watt. So what is the relationship? between the heating performance factor for heat pumps is the same type of relationship with the COP. You have the factor to unit conversion. So let's put it to test. Now I'm going to solve this problem in a second, but first let me show you. You also have energy guide labels. Here is one that is both a heat pump system as well as the traditional vapor compression refrigeration. So what we have is for both cooling and heating applications. It's a split system, probably goes in a house. You have the outside unit, indoor unit. You don't really want to call the outdoor unit anymore the condensing unit because you switched facility. What happens in that heat exchanger? And outside, what happens in the summer? It's condensing the refrigerant. What's happening in the winter? It's evaporating refrigerant. So they just call the inside unit, and the outdoor unit, the outdoor unit. Okay, so here is their SEER. Hey, that looks pretty impressive, a 15. And here is your heating seasonal performance factor, 8.2. So we want the most efficient, the highest SEER, the most efficient, the highest HSPF. All right? All right. Now let's solve this problem. You say that the heat pump has a HSPF of 8.2. What is its coefficient of performance? And these are the conversion factors that you'll need. So I'm going to pause. I want you to calculate it. Last time we did this here, didn't we? So let me pick it up here. So the HSPF is for a heat pump is the same basic definition as the COP of the heat pump. It's just that this Q dot to the hot is not the same as that Q dot to the hot. I like to think of the W dot ends are being the same units of either watts or kilowatts, but the numerator in the ratio is BTU per hour instead of watts. And so if you want to make them equivalent, basically the COP of the heat pump is equal to the HSPF of the heat pump times really a dimensionless unit conversion factor, but it has a numeric value to it, 0.293. But that'll convert the watts and cancel with the BTU per hour. So a lot of people just multiply. They don't even forget the units. Why they multiply, I don't know. They just multiply by nearly a third, 0.293. It'll work. So anyway, for this problem, the COP of the heat pump is 2.40.